Hi, YouTube. All right, we're now going to be talking about Atwood's machine. This is review session number 6. Ladies and gentlemen, if you'd like to socialize, you can go out in the hallway to socialize. Right now, we're going to focus on physics, all right? Particularly Atwood's machines. All right. Let's say we have a pulley and a rope and 2 masses on said rope. Now, I would be shocked if there was not a single Atwood's machine on this test. All right. What an Atwood's machine is essentially anytime you have 2 masses that are hooked up by a string, are acting as one system. Okay. What I mean by that is, let's say we have like lowercase m here and then capital M here. All right. I want to find the acceleration of the system. Okay. So what you have to do is you have to look at all the forces. You have to look at all, the entire motion of the Atwood's machine as a. I didn't even touch it. All right, as a whole.
I think
okay?
your arm is sliding along at the bottom, or the pen is just too close to the screen.
Okay. So I want to know what is the acceleration of the system. The way you do that is by looking at all the forces that are affecting. All right, now it's just this. I'm gonna start closing this.
So funny. Maybe there's something on the board. I don't know. Like on the bottom. Yeah.
All right. All right. So what forces are acting on this system, guys? Gravity on each of them. Assume no friction. Assume it's frictionless.
Are they going to say that on the test?
Yeah.
Yeah, that would say it on the test.
Well, I mean, it said it on the practice test.
All right. FG1 and FG2. All right. What else is acting on the system? Tension. Yeah, we got tension. Tension up. FT1 and FT2. All right. Now, what we're going to do here, and again, we talked about this yesterday too, to avoid confusion, we're not going to deal with positives, like up is positive, down is, we're not going to deal with that. We're going to assume G is always positive, and we're going to deal with direction and how we set up our net forces. All right. We'll deal with that when we zoom in on one block. We get to what is tension. But for right now, looking at this at a system. Now, the reason why is because looking at this right now, you might be thinking, okay, well, gravity would be negative and tensions would be positive, and so you add them up, you subtract them, no problem. However, that's not the case. If you look, FG1 is actually pulling on FG2. All right? They're pulling against each other, and therefore they're canceling each other out. All right? And so you'd have to subtract them. So the way to do this is to visualize this by laying it out horizontally. So we have FG1, FG2, and then we have our 2 tensions pointing in towards each other. FT1 and FT2. All right? Now, to find the acceleration of a system, we have to look at the net force acting on the system. All right, so this gets to Newton's second law a little bit. We have F net of the system equals mass of the system times acceleration of the system. All right? And so we end up doing this. All right, net force. Well, net force is going to be, we add them all up, right? So we have FG1 minus FG2, because they're in opposite directions. All right? So we have FG.
Did I leave my phone? Is it raining? Yeah.
Go check.
All right.
I knew it was supposed to rain today. No one listened.
I'm going to go look outside the door. I'll be right back.
And then the mass of the system would just be little m plus capital M times AS. Now what about tension? What would happen to tension?
Cancel.
Cancel out, right? Because again, they're in opposite directions, so just like the forces of gravity, you subtract them. However, the thing about tension is that they're, according to Newton's third law, they're equal and opposite forces, right? And so these two will just cancel out since they're equal. Right?
Wait, question.
Yeah.
Why is it FG1 minus FG2?
Because you're assuming that FG1 is going to be bigger. And I would tell you that. And we're assuming it's going to be rotating, it's going to be accelerating in the direction of FG1.
Okay.
Now, if you are not sure about it and you just pick one, and you find that your acceleration is negative, that just means that the other one was bigger. It's actually going in the opposite direction that
Okay.
All right? So this all assumes that's going to be accelerating to the left. All right? But then we can solve for this stuff this way. But this is kind of what I'm trying to get at here, because we know the masses, so we can get the FGs, we can get the M's, we're good to go. All right? Any questions on that? So I guess to wrap it up, you would solve for acceleration by just FG1 minus FG2 divided by M plus capital M. All right? Just going to close out these. I don't even know what this is. Oh, wait, I do need that thing. Okay. Were they open?
No.
Good. All right. So that's the complete secret of science, and we're all done. All right, good. Any questions on how we get acceleration of the system? Okay. Let's do a little bit more complicated then. Let's go over here. Nope.
Okay.
Yeah, you made it.
Nope. All right. So if we have now I coined them a horizontal Atwood's machine, but again, nobody actually uses that term. We have
This is example 1.
Yeah, this will be example 1. All right, this will be M1 hooked up to a string. Then we have M2 on the other end of the string hanging there. We know that M2 is going to be bigger. All right, that's all we know. All we know is that M2 is greater than M1. All right, I want you to solve for the acceleration in terms of mass and in terms of acceleration due to gravity. Acceleration of the system. All right. In terms of mass and g. There you go. All right. I'm going to kind of walk through. All right. You have to think about what forces are acting on it. Assume this is a frictionless table. All right. We're going to have gravity going down. It'll be Fg1, Fg2. We're going to have normal force going up. And then we're going to have tension following along with the string. All right. So, I want you to tell me, what is the net force of the system? Well, let's take a look here. If we start combining forces, subtracting ones that are in opposite direction, yeah. So we find that a lot of this stuff cancels out, right? Fn and Fg are in opposite directions, right? So we subtract them, but they're equal. So that means that when you subtract them, they just cancel out. Ft1, Ft2, they're in opposite directions, so we subtract them, right? But again, they're equal, so they just cancel out. That only leaves us then with F net of the whole system equals to just Fg2. All right? And that is going to be equal to the mass of the system, so F net system, times the acceleration of the system. All right? And so finally, we can then solve for the acceleration by plugging everything in, where we end up getting m2g is equal to mass of the system, which is just m1 plus m2 times a of the system. So we end up getting a of the system equal to m2g over m1 plus m2. That make sense? This is the problem I'm anticipating would be on the AP test. Something like this where you have to only use variables, no numbers, and it's an Atwood machine.
Now, are all these equations like given to us so we don't have to show and derive them because that's not going to
What do you mean, what equations?
Any of them, like mass and acceleration or...
Oh, yeah. Guys, look at our equation sheets here. Some key equations from here is A equals F net over M. So Newton's second law is given. You don't need to derive that. The only other equation I really used in here was Fg equals Mg, which I'm pretty sure is given. Is that, yeah, around here, G is equal to Fg over M. So that's also given. Yeah.
If these are on the FRQ part of the test, how many points are there?
Wait, I'm sorry, what do you mean?
Like
Oh, what would the point breakdown be?
Yeah.
We're going to be really going in depth into point breakdowns on Friday when we kind of talk about that FRQ. But essentially, it'd be like, oh, they get 1 point for knowing that the net force is this. Or they get 1 point for knowing that these cancel out. They get 1 point for knowing that you're using the mass of the system, right? Something like that. Oh, and then 1 point for getting the correct answer. So it's usually like a 7-point problem. Only 1 point is for getting the correct answer. The rest of it is showing your work, starting from a clear idea, and working your way down. Generally, a clear idea is like Newton's second law, conservation of energy, and that kind of stuff. I'm erasing these plus ones, so that way nobody gets confused when they look at the notes. Yeah.
For like part of like deriving it, if we like laid it out, like would they give us like points for that? Maybe.
I don't know if they give you points, but it definitely shows that, like, a lot of times, like, in the rubric, they'll say, get 1 point for showing they know this. And that can be through an equation, that can be through writing it, or that can be from redrawing the diagram. That could count, and somebody grading would be like, okay, that'll be a point, right? And so, that's why the more the merrier, right? The more you can put down, the better. However, be careful, because on a lot of the lab write-ups, there's a point for not having extraneous measurements, like stuff like that. Go open your windows.
It's still raining.
Still raining.
Oh.
Wait, it's raining?
Yeah.
It's raining. So you can see over there.
We're just gonna rain tomorrow.
How do you...
All right, I'm glad you asked. We know how to find the acceleration of the system, but how do we find tension force? Well, lucky for Deb T, she was at the elevator problem review session. And so an Atwood's machine just turns into an elevator problem.
This is example 3.
This is example 3.
Example 2, I mean.
Nope, it's example 3.
What? No.
Oh no, you're right, I'm
One.
sorry. Example 3. Alright, so,
Yeah, what do you think it'd be?
you ever notice how like the labs sometimes jump around in number?
Yeah.
Yeah.
It's like, I don't remember what number lab this is. 25. Alright, let's get some numerical number crunching in here, alright? Let's say we have 10 kilograms and then 5 kilograms. Alright? That's it, okay. I want to know, what is the acceleration of the system? Okay? I love that. Teaching us this? Damn, do it.
That's it, right?
What? That's all you're given, yep.
subtract the larger one from the smaller one?
Yep. Yep.
Just kidding, that's...
Wait, but in the, wait, I don't get, you did the smaller one minus the bigger one.
What? I did lowercase m minus capital M?
Yeah.
Yeah.
Well, I didn't. You're assuming that capital M was bigger, which.
Well, it was lower down.
So? Could still be.
Oh.
Yeah. I guess that could be a little misleading, but. And honestly, as I was saying, it doesn't really matter. Because worst case scenario, you do it incorrectly, your acceleration will still be correct, it'll just be negative, that's all. And so, yeah.
What's the tension on the yeah, that's
Tension's equal.
Oh, right.
Assuming this is a massless, frictionless pulley, and it's going without slipping.
What happened? I got 14,000.
Who got 3.3?
I did.
Who got 10?
I got 3.
Oh, okay. So, yeah. Me.
I got 3.
All right, we got a bunch of different answers here. That's what I like to see. All right.
3.33.
Who didn't do it?
Let's figure this out. All right.
Which one do you subtract from which?
What?
Which one do you subtract?
Which one do you subtract from which? All right. Let's lay it out. All right. So we get 10 and 5. Now, which way do you think it's going to be accelerating? Left. All right. So I'm going to do this one, which is going to be 100 newtons minus 50 newtons. Now, we do have the tensions in here, which we don't know what the tension is, right? But we know that they're equal, and so they cancel out. Before you can solve for the tension, we need to be able to solve for the acceleration. All right? And so we end up saying F net, in this case, of the system is equal to 50 newtons. Because you 100 minus 6. That's going to be equal to mass times acceleration. All right? Now the mass of the system is going to be 15. So we get 50 is equal to 15 times A. So we get A is equal to 3.333 meters per second. All right? Any questions on this? Now that we know that, how can we get the tension in here?
Doesn't matter.
Well, which tension are you? Like,
Ah, which tension are you finding? Are you finding...
There's only one tension though.
Yeah, are you finding this tension? Or are you finding this tension? They're the same. Now, what that means, guys, is you can pick either block. It doesn't matter. As long as you pick one, you can solve for it that way. Alright, so let's pick the... Now, generally, if you have more than one block, you always want to pick the block that only has one string on it. Like if we had another one down here, you would want to use the bottom block because there's only one tension they have to contend with. Alright? But now, this whole thing just becomes an elevator problem. So let's zoom in on one block. So let's zoom in on one block. Alright. So, we're zooming in on one block here.
Yeah, now you just you're just having fun now.
Alright. We've now zoomed in on one block. Alright. So that means we have FG going down, and we have tension going up. We know the acceleration of this block is 3.33. Right? And so we can now set up an equation, right? So we end up getting F net equals MA. This is now going to be of this block, not of the system. This is where a lot of people get tripped up. Now that you know the acceleration of the system, the key jump, the key understanding, I want to make sure everyone's looking up here, is the acceleration of the system is equal to the acceleration of each block. Because they're connected, physically connected. Alright? So because of that, we then say, okay, well, F net is going to be tension minus force of gravity. Or wait, no, I'm sorry. What would it be? Because which way are we accelerating?
Negative.
Yeah, it'd be Fg minus tension. And that's going to be equal to 10 times 3.33. All right.
Force of gravity mass times gravity.
What's up?
Plug in the gravity.
Right. Oh yeah. So this would be then 100 minus Ft equals 33.3, and so we end up with a tension force equal to
Negative 66.7.
66.7. Positive 66.7.
Oh, yes.
Right? And now, one of the key things about this method, guys, is that in order to get direction, you can't rely on positive and negative signs. All right? You have to look at the situation. Newtons, yep. All right? That makes sense? Isn't this neat? I just figured this out like a couple weeks ago. I can do this.
It's like a black hole.
No, do the opposite.
I like
Okay, yeah.
Since we're going over this now, can we go over this problem again?
Absolutely. Is that the one with the unknown mass?
Yeah.
My pictures are on the brain.
Yeah.
Oh, no,
It's on the old test, actually. Yeah, so we're just going to do this right now. So this is from the Unit 6.5 quiz. Unit 6.5 quiz. For some reason, I don't know what it is, with 9th hour, I always forget to hand stuff back.
Thanks.
And so I have a bunch of your old stuff. I need to hand it back. I'll do it tomorrow for sure. All right.
Don't forget. So true.
That's like an 8
Can you remind me where I can fill more guilty bag?
What?
Huh?
What'd you say?
What?
I'm looking for an Atwood problem. What?
Huh?
Oh, how many people are here? One. Yeah. Get more and more every day.
All right.
True.
And there might be pizza tomorrow.
And I didn't want to go the first Monday, and I tried it. By the time I looked at my
This?
All right. We're now on example 65.2. All right. If we have an Atwood machine now with 3 masses. All right. Trey's masses.
65.2. Oh my god.
All right. Now, we're given that this has a mass of unknown. This has a mass of 4.6 kilograms, of course. And this is 4.0. Now we know that it's accelerating this way. Okay. I want you to tell me, how can we find the unknown mass? We know that the acceleration is 4.5 meters per second squared going that way. All right? How do we get the unknown mass?